Andy Norton from the Department of Mathematics at Virginia Tech, and I'm here to share an activity on learning linear algebra the old-fashioned way. So before we get into the activity, I wanted to share a little history. When we talk about linear algebra, you might have seen it used for things like solving systems of equations. You would certainly see more of it in college courses, and there are several courses on linear algebra. It's a pretty deep subject, and linear algebra is used to solve a lot of different kinds of real-world problems, very complicated problems, because these matrices that are used to solve systems of equations, they could be very big matrices, and oftentimes we get computers to compute them. But we're going to see how people originally computed these kinds of matrices to solve systems of equations by hand. This method is often called Gaussian elimination, named for a German mathematician named Karl Gauss. He lived around 1800 AD, but the method, Gaussian elimination, is kind of a misnomer because the Chinese, ancient Chinese mathematicians, they used this method almost 2,000 years before Gauss was even born. And the reason they had sort of this jump start on Western mathematicians is because of the Chinese rods, the way that Chinese represented numbers and did arithmetic. So let's start there. These are the Chinese rods. They represented numerals, and you can see that in the ones place, it looks just kind of like tally marks. But after you tally up to about 5, you might get tired of making tally marks. So if you look at 6, you use a horizontal line above to represent a 5, and then you only need one vertical line more to make the 6. So with 7, you see a horizontal line with 2 vertical lines below, and that's 7. You can think about it as like a 5 plus a 2, all the way up to 9, which has that horizontal plus 4 below it, so like 5 plus 4. When you get to the tens place, the orientations are switched. So now you can represent tens just with a single horizontal line, 20 with 2 of them, and so forth up to 50. And just like with the ones, you might get tired of tallying these tens. And so you put a vertical line above, and that represents a 50. So that vertical line with a horizontal right below it, that would be 50 plus 10, which is 60. And you can do something similar for 70, 80, and 90. So you see the ones place and you see the tens place, and they're similar, except you use horizontal instead of vertical, and then vice versa. Well, when you get to the hundreds place, you would actually go back to vertical again. So you would a 1 would look just like a 100, and a 900 would look just like a 9. So anyway, you would go back and forth between ones would be vertical, tens would be horizontal, hundreds would be vertical, thousands would be horizontal, and you just keep alternating back and forth. And this was maybe the first example of a base 10 positional system. They're talking about powers of 10, ones, tens, hundreds, and thousands, and each number has a place. They would write numbers kind of like we do, with the ones place on the right, and then the next over to the left would be tens, and the next over to that would be 100. So what I want you to do is take a break. This is just a little activity. I want you to pause this movie in just a second and try to represent the number 387 using these Chinese numerals. Now, you don't have the kinds of rods that the Chinese mathematicians would use. They would physically use rods, but we'll use toothpicks as just sort of like small rods that you might have at home. If you don't have toothpicks, you can use like dry spaghetti noodles, but you're going to need lots of them. If you use pencils or something like that, you're going to use lots of them. If you don't have any of that stuff, you can just make marks to look like these. But it's best if you have something physical that you can move around, like a toothpick. And try to represent that number 387 using these Chinese numerals. Okay, so you should have gotten something like this. Notice on the right side, just like us, they would put the ones place on the far right side. You have a 7. There's the 5 going horizontal. That horizontal line represents a 5 with 2 below it, so that's a 7. And then just to the left of it is your tens place, and you can see there's a 50 plus 3 more tens, so that's 80. And then you have 3 ones, which is 100. And you can go back and see those numbers represented here. Pause if you need to check, but That's the number 387. Okay, so going forward, let's see if we can do some kinds of arithmetic using these rods. So we'll represent one number in the top row and then another number in the second row, and we're going to add these numbers. But first, can you figure out what these numbers represent? So looking at these, there are two different 3-digit numbers that we're going to add. What are those numbers? And again, you might want to pause back here to see this screen so that you can figure out what these represent. But you're trying to represent those numbers for right now. We'll add them later. Okay, so these are the numbers you should get. The top one is 483, and you can see there were 4 in the hundreds place, and then there's 8 in the tens place. There's that 50 plus 3 tens below it, so that's 80. And then you have 3 ones in the ones place. Likewise, for the second row, you have 568. Okay, so now we're going to try to add them. So adding wouldn't be so different from the way that we add, because everything's lined up. The ones place and the tens place and the hundreds places are lined up. So you can add them and then just keep track of the place values. So try to add just using the rods, not using our Hindu Arabic numerals that you see up top, but using the Chinese rods. And I'll pause here so you have a chance to do that. Okay, so what would happen in that ones place? Looking back, we had a 3 and an 8, and we add them, we're going to get 11. And you can see 11 represented in the lower right-hand corner, but it's a 10 and a 1. Well, that's the ones place. A 10 doesn't belong there. The ones place only goes up to 9. So that 10 really belongs over in the tens place. Well, we already have 8 tens on the top row, and then we have 6 tens on the second row, and now we got one more 10. So there's going to be 8 tens, 6 tens, and then one more 10. That's going to make 15 tens. And so we can see that here. We just have the 1 left in the ones place, and now we have 15 tens. Of course, that looks like 150, right? There's a vertical line for the 100, and then you have 5 horizontal lines for the tens. Well, that 100 doesn't belong there. That's the tens place. The tens place only goes up to 90. So we've got to combine that 100 with the hundreds place. So you've got 4 100s in the top row, 5 100s in the second row, and now we're going to carry this extra 100. It's just like carrying the 1 in our Hindu Arabic arithmetic, but we can see clearly that 1 is 100. So we've got 4 hundreds plus 5 100s plus this extra 100, and that's going to make it 1,000. Well, look here. That horizontal line on the left-hand side is 1,000. So it actually is already going to get bumped up to a higher place value. And when it's going to be in the thousands place. So there are no hundreds in this picture. And I can tell that because remember the ones and hundreds places will be vertical. And there are no vertical rods here. So I can tell, even though I don't have a 0, see in that top number, 1,051, we have a 0 for the hundreds place. We don't have a 0 with the Chinese rods. But we know that it's the hundreds place that's missing because we would expect to see a vertical line in between the horizontal lines, and there isn't one. So we've got 1 1,000, no hundreds, 5 tens, and then a single 1. So that's 1,051. Okay, so what we're going to do now is use something similar to solve linear algebra problems, to do what we might call Gaussian elimination, except the Chinese called it the way of calculating by arrays. So arrays are like matrices. You can think about array as just sort of like a grid with rows and columns, but we're going to use this array to calculate. And that's what how they referred to it in the 9 chapters of the mathematical art, where this method of what we now call Gaussian elimination or row reduction, where it was first introduced. And notice that was around 263 AD, so long before Gauss, who lived around 1800 AD. So anyway, we're going to solve this ancient problem. And the way that in these ancient mathematics textbooks, before we had algebraic symbols like X and Y to represent formulas, the way that mathematicians would demonstrate their methods is to solve particular problems, often real-world problems. So here we have a real-world problem, And in showing the solution to this problem, what the mathematician is doing here is really kind of showing off a method that they could use with all kinds of problems. They're just using this as an example. So the problem involves 3 types of corn, and we're given some hints about these 3 types of corn. If you have a bundle of the first, two bundles of the second, and 1 bundle of the third, together they would make 39 measures. And then we know that if you take 2 of the first, 3 of the second, and 1 of the third, you get 34 measures. And then finally, we know if you take 1 of the first, 2 of the second, and 3 of the third, you get 26 measures. So that should be enough information for us to figure out how much there is, how many measures there are of each type of corn. So the first type of corn, the second type of corn, and the third type of corn, how much a bundle of each type would measure. How many measures are in each type of bundle. So that's what we're trying to figure out. And so we need a way to represent that. And what I'm suggesting is that the way that the Chinese represented their numbers with rods lent itself to solving these much more advanced problems, these linear algebra problems. So we should be able to represent this problem by laying out rods, almost like we laid out the addition problem before. So see if you can think of a way to represent this problem. And we have 3 different pieces of information, and we should be able to represent each different kind of information row by row in an array. So I want you to pause the video again and just represent the problem. You don't have to solve it. Just try to represent the problem using rods, and then later we'll see how we can manipulate the rods to get a solution. Okay, so you should get some representation like this, where you have 3 of the first type of bundle, that's in the upper left, 2 of the second, 3 bundles of the first kind of corn, that's in the upper left, plus 2 bundles of the second, plus 1 bundle of the third, and then you can see on the right-hand side, that's supposed to be equal to 39 measures. That's why it says 39, 3 horizontals, and then the 4 verticals below a horizontal, so that's the 9, so 39. So we see the 3, 2, 1, 39 representing that first piece of information. And then likewise, we can represent the others. 2 bundles of the first kind plus 3 bundles of the second kind plus 1 of the third kind equals 34. That's what the second row says. And then the third row says 1 of the first kind plus 2 of the second plus 3 of the third makes 26. And we want to figure out now how to manipulate these rods. We're not going to have to write anything down. We can just manipulate the rods as the ancient Chinese mathematicians would have done to try to figure out how many measures each type of bundle would be. So how would we do that? I want you to think about that, and then I'll show you a way to do it, but you might do it a little bit differently, and we'll see if we can get at least a partial solution to this, and maybe you can figure the rest out on your own. Okay, so what I've done here, going from that first picture to this picture, the only thing that changed is the second row. So if you look at the second row, the numbers are a lot bigger. And that's because what I've done is I've duplicated that row. I've essentially multiplied everything in that second row by 3. So whereas there used to be a 2, 3, and a 1 in the second row, now there's a 6, 9, and a 3. And then where there used to be a 34, that it's supposed how many measures it was, I've tripled that. When you triple 34, you get 102. So on the right-hand side of the second row, you can see 102. There's a vertical line for the 100, there are no 10s, and then there are 2 vertical lines for the 1, so that's 102. So I just tripled that, but why? What's the motivation for tripling that second row? Well, if you look, if I triple the second row, that means that first column in the second row is a multiple of 3 now. And the first row has a 3 in that first column. So if I keep subtracting the first row from the second row, subtract all the things in the first row from all the things in the second row, kind of like we did for addition, just subtracting instead of adding, I'm going to keep doing it until I can wipe out that first column. The first column in the second row. The first column in the second row has a 6 in it. So if I take away the values from that first row twice, then that first column in the second row will disappear, and then I can see what I've got left. So you'll see the 6 is gone, but now in the second column, I've taken those 2 away from the second column in the second row. There was a 9. I took those 2 away twice, so I'm left with 5. And in the third column, I took those 3. I had 3 in the third column of the second row, and I've taken away 1 above it twice, so I'm left with 1. And then I used to have, that first row has 39, but I'm taking it away twice from 102. So I used to have 102, but after I take 39 away twice, 39 twice is 78. When I take that from 102, I should be left with 24. And that's what you see represented there. And so notice there's no first column in the second row now. And I can do something similar to the first column in the third row. And the reason I'm doing this is I'm trying to get the equations to be simpler. I'm trying to get these representations to be simpler to where maybe eventually I just have one of these types of corn left, and then how many measures it's supposed to be equal to. So like I did before, I'm going to, I took that third row, see the third row there, I'm going to triple it again, and I end up with this. So I've tripled the third row. So now that I've tripled it, I can take the quantities in that first row away from it until the first column is gone. But notice I only have to do that once now because the first column only has a 3 in it. So if I take away the first row from the third row, that first column is going to disappear right away, and I'm left with this. So notice I've got the second and third rows have nothing in the first column. And now what I'm going to do is I'm going to focus on combining these 2 rows with each other until I get rid of the second column. Well, in the second row, in the second column of the second row, there are 5 units there. And in the second column of the third row, there are 4. I'm going to multiply that whole third row by 5, and it'll end up looking like this. The 5 becomes a 20. The 8 becomes a 40. And the 39 becomes a 5 times 39, 5 times 40 is 200. So 5 times 39 is 5 less than that. So that's 195. And that's what you see there on the lower right side. 1 vertical for the 100, and then 90, and then 5. So I've multiplied that third row by 5. And now I want to eliminate the second column in the third row by taking away the second row from the third row a multiple of times. So I need to take away that second row from the third row 4 times to get rid of that 20. I've got to take away that 5 from the 20 4 times. So I'm going to take it away 4 times, and that second column is going to disappear. But I took away the 1 in the third column of the second row from the third column in the third row. I've taken that away 4 times as well. So the 40 turned into a 36. And also I took the 24 on the second row away from the 195. I took it away 4 times. Well, 4 times 24 is 96. So I took 96 from 195, and I'm left with 99. And look, now I know that 36 bundles of the third type of corn is 99 measures. So I can kind of read right there how much a bundle of the third kind of corn is. 36. 36 of that third type of corn, 36 bundles of that third type of corn is 99 measures. So if I want to find out how much is 1 bundle of that third type of corn, I can just divide by 36. So I do 99 divided by 36, and that should give me 1 bundle of the third type of corn. So 99 divided by 36, let's see, 2 times 36, that's 72. So it's 2 wholes. So there are 2 whole measures, and then I'm left with 27. Well, 27 out of 36, that's 3/4. So 2 3/4. So 1 bundle of the third type of corn is 2 3/4 measures. So that gives us some of what we wanted, and we could actually use that information in the second row to figure out how much there is of the second type of corn, if you think about that, and maybe then figure out how much there is of the first type of corn. Or you can continue doing the kinds of manipulations we talked about until you isolate the second type of corn or isolate the first type of corn. So you can play with the rods to kind of get these solutions. All you've done is manipulated the rods that the Chinese use to represent their numbers anyway, but now it's a little bit more abstract because you're trying to find unknown quantities, and that's where linear algebra came from. You can find more resources on this at these websites. The first one goes through in maybe a little more detail the solution to the problem we just talked about, and the other two talk more about Chinese rods in general and how Chinese people use them, ancient Chinese mathematicians use them to solve different kinds of problems. Thanks for doing this activity, and I hope to see some of you later on a Zoom meeting. You can share what you did with the rods to get solutions and share your questions as well. See you then.